So, hi everyone, welcome to the ICTS String seminar. Today we are happy to have David Tong from Cambridge, who will be talking to us about Chern-Simons theory for the Indian Ocean. So, over to you, David.
Thank you very much. Let me just get my slides up. Okay, can you see the slides?
Yes. Yeah.
Oh, good, very good. All right, thank you very much for the invitation. It would be much nicer to actually be there in person, but this, I guess, is the next best thing. This, I guess, is going to be a little bit of light entertainment for you. I want to tell you about a paper that came out last September, looking at some simple aspects of fluid dynamics, and in particular some aspects of fluid dynamics that apply in the ocean and the atmosphere. And it was motivated by some work that I'll put the citations up a little bit. Some work from maybe 5 years ago. I think this started. And there were a collection of, I think, condensed matter-ish people, fluid dynamics-ish people, who wrote a beautiful paper suggesting that there were some connections between topological insulators and the large-scale motion of the ocean and the atmosphere. And the key really dates back, I guess, to the 1800s. In the 1800s, it was realized that there are chiral modes in the ocean. And I'll review this at the beginning of the talk. There are two sets of chiral modes in the ocean. There's one set of chiral modes that go around land masses. So they're coastal waves, and they're coastal waves that go clockwise in the northern hemisphere, meaning the land is to the right of the wave, and go anti-clockwise in the southern hemisphere. It's like this myth about the bathtub. You know, if you pull the plug out of the bathtub or the sink, the water's supposed to go one way in the northern hemisphere and the other way in the southern hemisphere, driven by the Coriolis force. This is the true version of that story. There are these modes that just go one way in the northern hemisphere and the other way in the southern hemisphere. And then in the 1950s, it was understood that there are similar chiral modes at the equator. There are modes at the equator that just go west to east. And if you know a little bit about topological field theory, especially in 2 dimensions, you'll know that chiral edge mode is the smoking gun of a topological state of matter. Quantum Hall effect, for example, has chiral edge modes. 2D topological insulators have chiral edge modes. So it does sort of open the question, could there be some connection between the topological phases of matter that, you know, we care about in high energy physics and quantum condensed matter community, and something much more grounded? Maybe grounded is not quite the right word for the ocean, but something much more mundane and down to earth, which is the dynamics of the ocean. And a few years ago, this was answered, and the answer was yes. Roughly speaking, what these people did was compute a Chern number for the ocean, but really a Chern number for the in the momentum space of the waves of the ocean, roughly speaking. And they argued that an ocean in the northern hemisphere had Chern number 1, an ocean in the southern hemisphere had Chern number -1. The usual story about topological phases of matter is that whenever the Chern number jumps, there's some corresponding edge mode. So this was the original story. There were a few things I didn't like about it. Firstly, if you know a little bit, and this is a statement just for experts, if you know a little bit about topological phases of matter, you'll know that you're supposed to compute Chern numbers in momentum space when your system is on a lattice, because then you have a Brillouin zone and momentum space is compact, and it makes sense to compute Chern numbers. And somehow all of that was ignored when applying it to the ocean, with lots of let me say, slightly unpleasant consequences as well. So it wasn't quite clear that what they were doing was the right thing to do. In addition, there was some weirdness about these waves at the equator, which, if I have time, I'll mention at the end. But there were some things about the waves at the equator that were unfamiliar to me, and I didn't understand, and I wanted to understand them better. And so I thought it would be nice to just rewrite the equations that govern the ocean in a form that's more familiar to me, and I hope to people here. So that's what I did. I understood some things better. I still don't understand those equatorial waves at all, but I think there's a nice story that I will try to tell you. So let me start with, okay, very good. Let me start with a rather nice video that I downloaded from the NASA webpage. So this is a video. As you can see, this is the Pacific Ocean. I couldn't find one for the Indian Ocean. This is the Pacific Ocean. This is America. This is Ecuador here. And I'm going to press play shortly. The video will last about 20 seconds. But I want to explain what you're looking at when you see it. So the video will last 20 seconds. That 20 seconds covers a 2-year time span of the ocean. And what you're looking at here is the height of the ocean above the average, measured to within an accuracy of 1 centimeter. The red, I think, is plus 20 centimeters. The blue is minus 20 centimeters. But the accuracy is 1 centimeter, which is kind of astonishing because there are these waves in the ocean that are tens of meters high. But this is what we would call low energy effective field theory or long distance effective field theory. You average over all the fast fluctuations. The waves come and go very quickly. But over very large time scales, it makes sense to say what's the average height of the ocean to within in this case, remarkably 1 centimeter accuracy. And you'll see that on these very large timescales, there are features in the ocean. And the features that I want you to look for are the following. Firstly, the waves on average drift west. They go leftwards. But every now and then, you'll see this chiral wave at the equator, which will be a much more fast-moving wave going along the equator. And then when it hits Ecuador, things get a bit messy, actually, because fluid mechanics is generally messy. But one of the things you'll see is that the waves travel upwards in this direction and downwards along this direction. These two are the coastal chiral waves. Obviously, if they kept going, they would go clockwise around the landmass in the northern hemisphere and anti-clockwise in the southern hemisphere. All right, so that's what we're looking for. And why isn't it working? This is embarrassing. Oops. Having told you what we're going to see, I don't think we're going to see any of it. I'm really sorry. My video is not working. Okay, I really apologize. I'm not sure there's much I can say. That there was a beautiful video, none of which you're going to see. I'm sorry. Let me just tell you some equations instead. All right. So these are the equations that govern the motion of the ocean on large distances. They're called the shallow water equations. And let me just walk you through what these equations are doing, assuming that, like me, you know fluid dynamics. So they're equations in 3 variables, and each variable lives in 2 + 1 dimensions. So they're equations where the variables depend on x and y, which is the position along the oh, thank you, Deepak. Okay, Deepak has something that you can look at when later. Thank you for that. So we've got 3 variables: height, velocity in the x direction, and velocity in the y direction, each of which is a function of 2 space and 1 time coordinates. The equations, I'll walk you through them shortly. They can be derived from the Navier-Stokes equations. They're derived from the Navier-Stokes equations by getting rid of viscosity to begin with. That's irrelevant for this story. And then basically integrating over the z direction of the fluid. So the key assumption that goes into this is assuming that the height of the fluid, the z direction, is much smaller than the extent in the x and the y directions. So they're called the shallow water equations. They're a very badly named set of equations. In particular, the shallow water equations apply to the ocean, even though it's several kilometers deep and not particularly shallow. They also apply to the atmosphere, even though the atmosphere is not made of water. But they apply to fluids where they're thin and long, basically. So these are the equations. Let me walk you through them. The first equation tells you how the height changes. The capital D is something like a covariant derivative. It's what's called the material derivative in fluid mechanics, and is given along the bottom here. And the first equation is just capturing the fact that the mass of the fluid is conserved. And so what happens is if all the fluid piles up at some point, so grad dot u is non-zero, the height has to grow at that point. And if all the fluid is moving away from one point, the height shrinks. So that's what the first equation is telling us. The second two equations are just F equals ma. So the left-hand side is the acceleration. The right-hand side has the two forces that are at play here. The two forces are the Coriolis force and the gravitational force. So both of them very familiar. F is the name that fluid dynamicists always give to the strength of the Coriolis force. It's a parameter which has dimensions of inverse seconds, and it's roughly 10 to the minus 4 inverse seconds. It's the strength of the Coriolis force. I just Googled before I joined the talk. It's a factor of 4 smaller where you are in Bangalore than where I am in London, because the Coriolis force is strongest near the poles and vanishes when you hit the equator. And you can see what's going on here. The Coriolis force is very much like the Lorentz force for a charged particle in a magnetic field. In particular, the acceleration in the x direction, that's u dot, is equal to F times the velocity in the y direction. And meanwhile, v dot is minus the velocity in the x direction. So this first term is very much like Coriolis force, Lorentz force. Also rather nice because, of course, it's the Lorentz force in a magnetic field that drives the physics of quantum Hall effects. Here it's the Coriolis force doing something similar. And finally, this is the gravitational force. Again, it's clear what's going on. If you have a height difference, what will happen is the fluid will want to push downwards, but the fluid is incompressible. So in pushing downwards, it's got to push in, set up a velocity in that direction. So that's why the acceleration is proportional to the change in the height. All right, so these are the equations that we are going to be discussing. Are there any questions about this?
Yes, I have a question.
Yeah.
So the first equation seems to be that if you take the right-hand side to the left-hand side, it is something like the total derivative of h with respect to t goes to 0. Isn't that correct?
It's a continuity equation, the first equation, and I'll describe that in some detail later. Yeah. Yeah, it's a conservation law.
Yeah, that's what I meant.
Yeah. And as I said, it comes from conservation of mass. So the fact it can be written as a continuity equation is not surprising. But it's going to be an important point and one that I'll highlight later. Thanks.
Thanks.
Other questions? All right. So these are the general equations. For many purposes, it's useful to linearize them. The equations we see here are nonlinear. Actually, let me just go back quickly. These are nonlinear. The nonlinearities you can see on the right-hand side of this equation, and also they're buried in the material derivatives here. There's nonlinear in U. There are some features for which the nonlinearities are important. These equations have shock waves, for example. They exhibit turbulence. All of that needs the nonlinearities. But for most of the interesting physics for the climate and the ocean, the linearized version is sufficient. The linearized version means that you set an average height of the ocean, that's capital H, and then you look at small fluctuations of that height that I'm going to call eta. So our new variables are u and v, velocity in the x and the y direction, and eta, which is fluctuations of the height. And here are the linearized equations. All right. So
David, I have a question, please, David.
Yes, please.
Is there some simple Lagrangian from which these equations are derivable, because you have put viscosity to 0, right?
Yeah, that's right. So there is a not particularly simple Lagrangian that was written down in the 1960s, I'm going to say, that yes, exists. But what I'm going to show you at the end of this talk is that there's a Lagrangian for these equations that's extremely familiar, that you know very well, Spencer, and it's the Lagrangian of a gauge theory. So that's where we're going to go.
Okay, thank you.
Other questions? All right, let me just tell you some simple solutions to these equations. So the equations are written at the top here. And we're just going to look for wave solutions, which means we'll look for Fourier type modes where the height fluctuates with some frequency omega and some wave vector k. And similarly, the velocity fluctuates with some vector frequency omega and wave vector k. Plug this ansatz in the middle into these equations at the top. Do some rearranging, and you'll find that you end up with a rather simple eigenvalue equation of the kind that starts to look familiar from things that we all do more often. So I've introduced a vector that I've suggestively called psi, rather like a wave function or perhaps a Dirac field. It's a three-component vector consisting of the height, suitably rescaled, and the velocities. And then you get the momentum appearing on the left-hand side. The whole thing looks rather like a Dirac equation at this point. And it's not a familiar Dirac equation because it's a three-component vector rather than two-component or four-component. Nonetheless, you can see it's something linear in derivatives because you've got the linear in momentum here equals energy times pi. So it's not dissimilar to the Dirac equation. Also, if people know what the Chern insulator is, it really starts to look something similar to the Chern insulator, which is, I think, was the kicking off point for the papers that started thinking about topology in this context. All right, so this is the equation that we want to solve. It's a very simple equation to solve. And
I have a question. Just can you go back to the previous slide?
Yeah.
Yeah, so in this psi column, this column that you have written,
Yeah.
it got, the first thing is a height and the rest of them are velocities. So how are the how are the dimensions are going to be matched?
Because I've got this rescaling here. So G has dimensions of acceleration. You divide by h, which is the average height. So this thing in the square root has 1 over time, dimensions of 1 over time. Okay. So the dimensions of everything here is the same.
Okay, thank you.
Yeah. Oh, I should also say that I introduced a speed here. The speed is c. If you know a little bit of fluid mechanics, this is the typical speed for surface waves in a fluid. So square root of g times h. All right, so very simple to solve. Here are the solutions. And there's two classes of solutions, one of which is familiar and one of which, from a high energy physics perspective, is rather unfamiliar. So there are some solutions that have a dispersion relation which looks very familiar from a relativistic context. So this looks very much like the E squared equals P squared plus M squared dispersion relation of a massive relativistic particle. We'll come back and see that connection later, where what we would call the mass of the particle or the gap of the frequency is set by the Coriolis force F. So F is this distance here in the frequency gap. These waves, they're waves that are observed in both the atmosphere and in the ocean, and they go by the name of Poincare waves. So these are rather fast-moving waves. When the wavelength is short, so k is big, the dispersion is roughly linear. So they're sort of go approximately as omega is proportional to k at large wavelengths, but they're gapped at small wavelengths.
So David, I have a question here. Sorry to interrupt. In what you said, so you're looking at phenomena over a short scale because f is a constant, and as you explained, f changes. Is that right, sir?
That's right. So there's some payoff here. If you look over a scale of less than, say, 100 kilometers or so, you can probably extend that to a few hundred kilometers. F is roughly constant, and so I'm certainly looking at those scales. Actually, yeah, let me just stop there. I think that's the right approximation to have in mind.
Okay, thank you.
The slightly more surprising...
Hello?
Hello, yes, please.
Yeah, so the F vanishes at the equator. Is that what you said?
That's right. So if you're at the equator, you have to do something a little bit different. Naively, it looks as if these just become gapless modes, that this becomes a cone. that goes down. The right thing to do at the equator, though, is to take f to be varying as a function in the north-south direction, and then solve these equations with f varying.
So this would be like some kind of, so equator would be like something like a domain wall where the mass vanishes, is that?
That's right. It's very much like a domain wall where the mass varies. Yeah, exactly. Yeah. And in fact, those chiral modes, which I failed to show you because my video didn't work, that go west to east along the equator are very much like the chiral modes that Jakiv and Rebbe discovered on a domain wall.
Okay. Thanks.
Sorry, so in the equator, you're saying that omega is just CK?
Let me, I was not going to discuss the equatorial waves, but I have some slides. So let me finish this, then I'll go and show you exactly what happens at the equator. Yeah. All right. So what else do we have? The slightly surprising feature is that there's what a condensed matter physicist would call a flat band. In other words, there's a set of waves that don't change in time because their frequency is zero. It's what geophysicists call geostrophic balance, and it's actually fairly easy to see from these equations up here. So if you set the time derivatives to zero, then all you have to do is balance these two terms against each other. And what's happening here is that the ocean isn't flat. The ocean has some height differential, but the current going this way is causing a Coriolis force, which perfectly balances the gravitational force that would want to push it down. And the upshot is that you can have solutions in the ocean where these two forces balance, and the ocean doesn't lie flat, but perhaps rather surprisingly has some non-zero profile on its velocity, on its surface. For what it's worth, the actual ocean in the Earth varies by plus and minus 1.5 meters in its stationary state compared to what you would naively expect because of this geostrophic balance. So this is something which is the dominant force isn't quite the right word, the dominant feature in flows in the ocean. All right.
Sorry, can I ask, so you've not been talking about boundaries, but do the boundaries matter for these modes, these flat bands and so on?
Very good. So at the moment, I've not been talking about boundaries. I have two extra things I can tell you. One is about boundaries and one is about the equator, both of which need a little more care. So let me do it in that order, actually. Let me tell you about boundaries and then let me tell you about the equator. Other questions before I go on? But by the way, it's nice to see that the subject is completely different, but the names are exactly the same. Some things, some things don't change. All right, let me tell you about what happens with a boundary. So this is a calculation. I went back and looked at the original paper. Actually, it's a beautiful paper. It's a calculation of by William Thomson, better known by his later name of Lord Kelvin, from 1879. And the calculation is the following. Let me put a boundary here. Now, u is the velocity of the fluid in the x direction, and I've got a boundary at, say, x equals 0, which clearly means that on the boundary, the velocity of the fluid better be in that direction better be 0, because nothing can go into the land. So in fact, what Kelvin suggested is that we should look for solutions where the velocity in the x direction is 0 everywhere, just as an ansatz, with the velocity in the y direction, that's v, and the height varying with some Fourier modes in the y direction with some profile in the x direction. So that's the ansatz we're going to make. If you plug it into the equations at the top, so here are the equations. Here's the ansatz. If you plug it into the leftmost and rightmost equation, you find the following, that the frequency and the momentum, it's not quite the momentum, but okay, you know what I mean, are linearly related with a plus or minus sign. And the profiles of the height and the velocity are related in the following way. If I now plug this into the middle equation where, again, time derivatives, well, u is 0, so the left-hand side vanishes, then it tells you that the height and the velocity have an exponential profile in the x direction, given by the following. The key is that for this to be a normalizable mode, the exponential profile of the height better decay exponentially, not grow exponentially as you move away. That fixes the sign in the omega versus k relation, and you're only allowed one of these signs, not the other sign. So the upshot is that if you're in the northern hemisphere, where F, the Coriolis force, is positive, then you're obliged to have omega equals minus ck, which means it's a chiral mode and propagates downwards, meaning that... Sorry, I've got a fire alarm here. And it's gone off. All right, very good. So the wave propagates southwards, meaning that the coast is always to its right. So this is what I said before, that the chiral wave will go in the clockwise direction, always with the coast to its right. In the southern hemisphere, F is less than 0, and this gets changed to a plus sign, and it goes the opposite way in the southern hemisphere. So these are called coastal Kelvin waves. They're observed. They've been observed for many, many decades. Something that I think is rather lovely, that the calculation that Kelvin did is almost identical to the calculation that Jakiv and Rebbe did 100 years later, when looking at fermion zero modes in the presence of domain walls, for example. So I think it's it's a lovely example of the unity of physics. It's also a lovely example of how you can get famous by repeating a calculation a century later and just doing the same maths. All right. This was these chiral modes were the reason that, as I said earlier, a few years ago, people started trying to understand if there were some topological reasons underlying these. I'm not going to go through what these people did because I think there's a slightly better way of explaining it. But here are the two papers. The first one kicked this off, Pierre Delplace and company, talking about equatorial waves. The second one from just a couple of years ago gave an explanation for these boundary modes, these coastal Kelvin waves, also in terms of topology. All right. Are there any questions about these coastal waves? I will go and explain the equatorial waves briefly. Okay. Yeah, sorry, some data. I know I promised you. Any questions about the boundaries? And then I'll just quickly talk about equatorial, and then I'll tell you why gauge theory is useful for all of them.
Hi, David. This is Shaheen. I have a question.
Hi, Shaheen.
It seems that the coastal waves and the Poincare waves are sort of directly related if we consider some imaginary k for the Poincare waves. So if you please go back to the dispersion relation for Poincare waves.
Mm-hmm.
Okay, and if we take, for example, k is the two vector, it has one component k1 and the other k2, and let's take k2 to be I times something, and choose that something exactly such that the f squared term is dropping off. So do you have any comments on this?
No, I think that's just right. And without a boundary, you would throw that away because it would grow exponentially quickly in one direction, and you put land there to stop it growing exponentially quickly. I think that's exactly right. Yeah. And it's also clear that, and we'll see this later, that the coastal Kelvin waves do indeed come from the Poincare waves rather than from this flat band. So they are indeed associated to this. In fact, as you know, there's a conserved charge, the potential vorticity, that tells you they're related to the Poincare waves. Yeah.
And in the same way, the flat band is also a special wave, Poincare wave case where both of K1 and K2 are imaginary and they exactly cancel off F squared.
I'm less sure about that. Because then things would grow exponentially in some direction, and that's not the case for the flat band.
Well, this is formally what one can see from this dispersion relation.
Yeah, I'm less sure about that interpretation.
Okay. So thanks.
Let me just appease some data and tell you about the equatorial waves. So I won't tell you all the details, but here are the linearized equations at the top. And for the equatorial waves, what you want to do is solve them with the Coriolis force changing from negative to positive. You know, if we do domain walls in fermion zero modes and domain walls, we typically have some tanh function for the mass. Here, our geophysics friends just focus on a linear change in y, which is valid within, as I said to Suvrat, a couple of 100 kilometers of the equator. That's not a bad approximation to how the Coriolis force is changing. You know, it changes as the sign of the latitude. So linearly in y is not too bad. If you plug in this particular ansatz into these equations, something rather lovely happens, actually. The lovely thing that happens is you end up with a second order differential equation for v, the velocity in the y direction. And that second order differential equation is the equation for a quantum harmonic oscillator. And so you don't have to do any work. You just know that the profiles are Hermite polynomials. You know what the frequencies are. They're the gapped frequencies of the harmonic oscillator. This is what the modes look like. So there are Poincaré waves, as there were before. What was a flat band picks up a bit of a dispersion. It's no longer quite flat, but varies very, very slightly. These are known as Rossby waves. And if that video had worked, the very slow moving waves that were going westwards are these Rossby waves. And then there's two interesting modes, which are the chiral waves at the equator. One of them is called the Kelvin equatorial wave, goes west to east along the equator. And the other one is a bit more confusing, and I've not really seen anything like this before. It's a wave that merges between the Poincaré wave and the flat band. It's called a Yanai wave. Again, it's observed experimentally. I'm sort of a bit puzzled about the features of this Yanai wave and why it has the properties that it has. But that's the story. Does that answer your question, Sundata?
Yeah. So I'm just worried that how can you get all these three different solutions from a single equation? I mean, shouldn't the equations be giving you just a single solution?
No, what can I tell you? Maths is wonderful, and that's just the way it works. This is my ansatz. I've got omega and k are the things that are left unfixed, and you can see that it's an eigenvalue equation, and so you get different omegas and k's for each of these. But then there are these two functions here: the height in the north-south direction and the velocity in the north-south directions are also functions that you have to solve for, which turn out to be related to Hermite polynomials.
Here you seem to be having an omega, and in the picture you have different omegas and k's, right? I mean, the relationships are different for different Kelvin, Yanai, and Rossby cases, right?
They're different, just as they were before for the Poincaré waves, which had omega going as omega squared as k squared plus f squared, and the flat band, which had omega equals 0.
Okay, fine. Let's continue. Maybe we can.
I'm happy to hang around afterwards, and I can walk you through this calculation. It's a pretty calculation.
David.
Yeah.
So you mentioned about the dispersion relations, but the profiles, how far are they? Can you experimentally kind of check them? Is that feasible? Like these exponential ones or these harmonic polynomial ones? Is that, I mean, given the kind of accuracy that you were mentioning, 1 centimeter and so on?
I think so. So actually, I realized I should have shown this. I have a snapshot from one of the more interesting parts of the video. So this red stuff here, if this was playing, the red stuff would be moving fast in the from left to right. This is precisely the Kelvin wave, the equatorial Kelvin wave. So I'm not sure. I think you can get the fact that it drops off exponentially quickly. So you would expect this to be the ground state of the harmonic oscillator. It's a Gaussian profile. Yeah, I guess your question is, Rajesh, can you read off from this data that it's a Gaussian with a particular width? The width you can see by eye.
They're presumably fixed by all the parameters.
That's right. But I'm not sure how easy it is to read off from this data that it's a Gaussian. Here also, these waves here, if you could see them, you'd also see them propagating up the coast. These are the coastal Kelvin waves, which drop off exponentially quickly as you move away, at least in the simple model. Again, whether or not, or to what extent that mimics what's seen in experiment, I don't know.
Thanks.
Also, is the understanding that all these waves are coexisting together, or you get a linear superposition of
that's right. There's a linear superposition, and as long as you can trust the linear theory, yeah, you can just add them all together, and that's precisely what's seen here. The whole thing is, some complicated mess of things going this way, things going up, things coming backwards slowly, but yeah, just a usual linear superposition.
Oh.
All right, let me tell you about some. We'll see how far I get. All right, so this was the background. And Spencer asked right at the beginning, can we write down an action principle? Because action principles are things that you and I are familiar with more so than these differential equations. So that's the goal. How do we write down an action principle that captures these equations here? These are the nonlinear equations. And what I want to convince you is that the following action does the job. So it's a U1 gauge theory. It's in 2 + 1 dimensions. So the electric field is a vector, but in 2 + 1 dimensions, the magnetic field is a scalar. It's like BZ, if you like, for the magnetic field. So the first two terms are very similar to a Maxwell Lagrangian, with the exception that I've divided the electric field squared by the magnetic field. So these are U1 gauge field kinetic terms. The Coriolis force appears as a background charge for this U1 gauge field. So there's an A0 multiplying the Coriolis force. And then there's some other dynamical fields, two scalars that I'm going to call alpha and beta, that couple as a electric current to the gauge field with the following term. There are no kinetic terms for alpha and beta, so they're slightly odd from our perspective. So my claim is that this action for a U1 gauge field reproduces those nonlinear shallow water equations that we saw before. And you'll need a dictionary. The dictionary is the following. The magnetic field is the height of the fluid, and the electric field is the velocity of the fluid multiplied by the height with an epsilon symbol. So electric field in the x direction is velocity in the y direction, and electric field in the y direction is minus the velocity in the x direction. All right, so that's the claim, and it's a simple claim to verify. Figure out the equations of motion for this gauge theory. Use this dictionary. You find out you get the shallow water equation, but it sort of feels like it's just come out of the blue. So what I would like to do is give you some explanation for why this is a sensible thing to do, and why this is the right gauge theory to write down. So the next 10 minutes or so, I'm going to give you what I hope is some simple explanations for why this U1 gauge theory in 2 + 1 dimensions is the shallow water equations. Are there any questions about the claim?
So is there a dictionary for alpha and beta also?
This is the action. So you should minimize this action with respect to alpha and beta. You'll get equations of motion. That's what's needed. But they're not quite Lagrange multipliers. Actually, it's not true. I could integrate by parts, and any one of them I could think of as a Lagrange multiplier. But then the other one has a derivative hitting it. So there's some sort of interesting interplay here, but you should minimize this action with respect to A, mu, alpha, and beta.
Yeah, so sorry, I was asking whether there was a shallow water interpretation of alpha and beta, like you had for B and E. Is there a dictionary?
There is. It'll follow, actually. Yeah, I see. Yeah, given this explanation here, the equations of motion for alpha and beta will tell us. They're related to something like vorticity, as we'll see shortly.
Okay.
Other questions?
So is this a nonlinear action?
It's nonlinear for two reasons. One, there's an E²/B here, slightly unusual. And two, there's an A mu beta alpha here. So there's a triplet coupling here.
Yeah, so nonlinear actions usually, nonlinear dynamics usually lead to kind of chaotic behavior in appropriate regimes of the coupling constants. So do you anticipate something like that?
That's right. These full nonlinear shallow water equations exhibit turbulence. That's the chaotic behavior. All right, so let me explain how I wrote this down, why I wrote this down. So there's two things to say. That the first one is that if you're in 2+1 dimensions and you have a U1 gauge symmetry, you automatically get a U1 global symmetry for free. And it's a topological symmetry, and it just follows from the Bianchi identity. So if you expand out the Bianchi identity, it tells you that the following equation holds, where I've got, there's a typo, this should be an X1. But you can see that it's really telling you that magnetic field is conserved in 2+1 dimensions. The magnetic flux is conserved. If the magnetic field changes in some region, it's because there's an electric field, which is like a current taking the magnetic field away. All right, so a U1 gauge theory in 2+1 dimensions immediately has a conserved U1 current. And with the dictionary that the magnetic field is the height and the electric field is the height times the velocity, this immediately tells us the first of the shallow water equations holds. So the first thing to say is that setting up the shallow water equations as a U1 gauge theory, the topological current of the U1 gauge theory corresponds to the conservation of height in the shallow water equations. Okay, so very straightforward. All right. Next thing to say, by the way, all of this is going to follow from conservation laws. Of course, that's the thing we all do when we have some new theory to play with, is you understand what the conservation laws are, and the whole point is that the conservation laws of this are interesting, and interesting in the same way as the shallow water equations. All right, so the second, yes, please.
This term that you have E squared by B.
Yeah.
It looks funny. I mean, I don't think I've ever seen anything like it.
I've never seen it before. You know, the obvious thing to be worried about is what happens when B goes to 0. This looks like it's bad. When B goes to 0, things are bad because your ocean has run dry. B is the height of the ocean. And, you know, you would expect these things to go to 0, to be singular when there's no water in the ocean. And that's what's happening. So you shouldn't be worried about this. And it's worth saying we are used to having inverse terms in actions. The Einstein-Hilbert action has a g to the -1 in it when you contract the Ricci tensor to get the Ricci scalar. So just think of it like this. It's okay, because you should think about this as an expansion around B non-zero.
Okay.
All right.
There seems to be also something else a bit odd. B is, I would expect it to be a pseudoscalar, whereas H, I would think that it's a scalar rather than pseudoscalar.
Oh, that's a great question. And I'm really annoyed, Shaheen, because I can't remember the answer. I did go through and check all the discrete symmetries. In fact, not only that, I reposted my paper on the archive this morning with a section with all the discrete symmetries added. So you can find it in that new version.
So it will be out tomorrow, right?
Oh, I did it last night. So actually, maybe it's out today or tomorrow. I'm not sure. Yes, but I didn't check. Yeah, so I can just send it to you though, Shaheen. I don't remember the answer to that, but there is an answer. Yeah, it's good.
The Coriolis force is there, right? So it would break some of the discrete symmetries, presumably.
That's right. Coriolis force breaks time reversal. Yeah, of course. Yeah. All right. Second point about conservation law: the shallow water equations have a conserved energy. The conserved energy is given by the following. Actually, it's easy to understand. The first term is a half mv squared, where m includes the height. And the second term it is the gravitational energy, which is usually gz, but you integrate gz from 0 to h, and so you get a height squared. So both of these is just undergraduate physics, or maybe even high school physics terms: kinetic energy, gravitational potential energy. Using the dictionary, that translates into the following energy in terms of the electric and magnetic fields. That strongly suggests that the action is going to have this with a minus sign, as indeed it does. These are both topological terms and don't contribute to the energy. Okay, so that gives some explanation for why, given this dictionary, which was used to get the height conservation, this is the action to write down. All right. The next thing to look at is the electric current, by which I mean the thing that couples to A mu. So usually there's an A mu, J mu term. I want to understand what's happening here. So to look at this, we can look at Gauss's law. Gauss's law is the equation of motion for A0. If you evaluate Gauss's law from this, you get the following. This is the usual, what would be the grad dot E in Maxwell equations, but there's a 1 over B term because of this. And when you plug in the dictionary for the electric field in terms of the velocities, you find that this term here becomes the vorticity, where the vorticity is the, well, it's what's written here. In other words, whatever couples to A0 here has to be the vorticity shifted with the background charge, which is the Coriolis force. So I was asked earlier, what's the interpretation of alpha and beta? Well, the interpretation of alpha and beta follows from the dictionary. It's the vorticity. All right. And finally, let me just point out something odd about currents in fluid dynamics. And when I say currents in fluid dynamics, I don't mean currents in the way that fluid dynamicists mean currents. I mean currents in the way that we think of currents, conservation laws. And it's something which in some sense I've known for 20 years. And it was only when doing this project I sort of realized that there's something odd about this. So there are two conserved currents in the shallow water equations, both of which obey the continuity equation. One of them is the height, which has charge height and current height times velocity. And the other one is the vorticity, has this shift by the Coriolis force. So the vorticity is the charge and the current is vorticity times velocity. If you're in fluid mechanics, the conserved objects are always of this form. It's always some charge, and then the current is charge times velocity. But what it means is that unlike anything I've seen in high energy physics, the currents are not independent of each other. You see, it's not really two conserved quantities, it's sort of 1.5 conserved quantities. If you know the charge and you know the velocity, so I know this, say J0, well, the thing on the top line and this charge, then I get the final current for free. So said differently, the currents are always parallel to each other. The vorticity current is always parallel to the height current because everything comes multiplying the velocity. So I've never seen this before in a high energy physics example. It's always currents being completely independent. But somehow this is the key feature of the shallow water equations, that there are two currents, but they're parallel to each other. The proportionality constant is very famous in fluid dynamics. It's called the potential vorticity. And as you can see, it's just the ratio of the vorticity to the height. All of which brings me back to this action. So the whole point of having this strange coupling here, where the A mu is coupled to two scalar fields in this way, was precisely to reproduce the fact that the current J tilde, which couples to A mu, is parallel to the topological current of the gauge theory. So the equations of motion for alpha and beta just tell you that the topological current is proportional to this current here. So that's the reason for this slightly strange coupling. Having said that, it's simple just to compute the equations of motion for this action and show that they reproduce the shallow water equations. All right. Any questions about this? And then I'll try and show you what this action is useful for, and also reduce it to something that you've all seen before, which because it's a little bit unfamiliar at the moment. Any questions? All right, so let's have a look. To reproduce some of the things I told you at the beginning, we're going to linearize this action. Deepak.
Yeah, I just want to clarify a couple of things. You have E, which is a vector, right?
Yep.
And it is related to the height multiplied by the velocity. And B is simply the height. And what are the components of the gauge field again? A0 and A1 and A2.
You know that you don't get to ask that question because it's a gauge variant question. So E and B are written, of course, in terms of A mu in the usual way. But you're not allowed to ask that question even in QED. There's no meaning to this because you pick a different gauge and you'll have to give you a different answer. So the same is true here.
No, I mean, okay. I mean, there should be some gauge transformation of these variables, right? Did you already show that yet, or did I miss it?
No, this action, of course, is invariant under gauge transformations. It's invariant under gauge transformations. A mu goes to A mu plus D mu something, because if I integrate by parts, you can see that this current obeys D mu J tilde equals 0 precisely because of the epsilon symbol and the two derivatives.
Right, and so E and B are not charges transforming under that symmetry.
E and B are the usual components of F mu nu in high energy physics. They're, B is the curl of D1A2 minus D2A1, E something similar.
Okay, so that's what E and B are in this case. Okay.
Yeah, E and B you should think of as functions of A mu, and the action you should minimize with respect to A mu, as usual in Maxwell theory, not with respect to E and B.
Okay, but B is one component and E is two components, right?
That's right. Yeah,
just like you would have in
just one dimensions.
Right. Okay. All right. Thanks.
Yeah. I have a naive question.
Yeah, please.
A0 is not a scalar, right? A0 is the time component of a vector, right?
That's right. Yeah. So this isn't relativistic.
Well, even I mean, so you're saying in the non-relativistic context it becomes a scalar?
What do you mean by a vector? Normally you mean by a vector that different components rotate into each other under some symmetry. But that symmetry is Lorentz symmetry, not rotational symmetry. So in that sense, A0 becomes a scalar. There's a slightly different way to say this, which is that strictly speaking, F should be a two form over space. You should think of F as a two form. And then what's really going on here is that this is the integral of a three form over a three-dimensional space. So if you want to sort of have a slightly more mathematically sophisticated way of looking, that's the way to think of this background charge.
What is F?
10 to the minus 4 inverse seconds. It's the strength of the Coriolis force, but you really might want to think of this, if you're worried about these kind of issues, as F dx1 wedge dx2 as a two form over space, F times a volume form.
No, I mean, how are they related to the H's, the heights and the alpha, beta, whatever? I mean,
F is a background parameter, strength of the Coriolis force, not a dynamical variable. B is the height.
If it's a strength, it must just be a coupling constant.
That's right. Yeah, it's just a coupling constant.
Yeah, so in that case, how do you say that it's a two form?
It's a two form coupling constant.
Okay.
Yeah, just a constant background two form, if you want to be fancy about it. But there's no need to be. You can also just think of it as a constant background charge.
Okay.
All right. So how am I doing for time? Okay, 4 minutes. We will get there. So I'm going to linearize this action, and I'm going to linearize about some fixed background magnetic field. So B is equal to H. And all the subtleties come from linearizing these alphas and betas. So these alphas and betas have to be linearized in the following way. There's some alpha hat and beta hat, which are some fixed number, actually some fixed function, really, as we'll see. And then P's and Q's are the things that fluctuate. And we'll see why I call them P and Q shortly. And the alpha hat and beta hat have to obey the following equation, where F is the background Coriolis force, strength of the Coriolis force. So if you plug this in, you get an action which now really is the Maxwell action, E squared minus B squared, when linearized. Then coupled in a rather strange way to these fields P and Q. And you see that P and Q appear with a PQ dot. So P is the momentum conjugate to Q, hence the name. And then the following slightly weird coupling. Okay. So it's an odd action. It's sort of strangely simple, and yet somehow I still have a sense I don't really understand it as well as I should. Nonetheless, it's very easy to write down the equations of motion, solve the equations of motion, and reproduce the waves that we saw before. So there are Poincaré waves, which after you integrate out the P and Q variables, turn out to solve the following equation. And then there's the geostrophic flat band, which is this slightly unfamiliar thing, which solves the equation at the bottom there. All right. So this equation includes both of these modes. And what would be nice to do is to somehow integrate out these P and Q variables to just get an equation or an action for electric and magnetic field. Now, that turns out, perhaps surprisingly, to be easiest for the Poincaré waves. I say perhaps surprisingly because usually we integrate out heavy modes to get an action for light modes. Here we're doing the opposite thing. We're integrating out the flat band to get an action for the gapped Poincaré modes. But the action is rather nice and something that I hope is familiar to everybody. If you do that, you can get an action just for the Poincaré waves, and the action for the Poincaré waves is precisely Maxwell-Chern-Simons theory. It's Maxwell-Chern-Simons theory where what we would call the Chern-Simons coefficient is the strength of the Coriolis force. It's well known that Maxwell-Chern-Simons theory has a gap. The spectrum of Maxwell-Chern-Simons theory is precisely the spectrum of the Poincaré waves. When you actually look at the profiles of the wave solutions, you reproduce the profiles of the Poincaré wave solutions. So those Poincaré waves do have a very natural action to address Spencer's question from some time ago, and the action is simply U1 Maxwell-Chern-Simons. The bells of Trinity College have just rung to tell me that I'm out of time. Let me very briefly tell you the punchline. Actually, I'll be very brief, and then people can ask for more details if you like. It's been known for a long, long time that if you take Maxwell-Chern-Simons, let me just put the picture up. If you take Chern-Simons theory, which describes, among other things, the fractional quantum Hall effect, then there are edge modes, chiral edge modes of the fractional quantum Hall effect, because there are edge modes of Chern-Simons theory when it lives on a manifold with boundary. You can show that those edge modes of Maxwell-Chern-Simons theory are precisely the edge modes that Kelvin wrote down in 1879, that mathematically they're entirely equivalent. All right, I can tell you a bit more details of that calculation if people are interested. All right, so to summarize, that these shallow water equations have what I think is a fairly natural rendering as a U1 gauge theory, a little unfamiliar because of the kinetic term, and more unfamiliar because of the way it couples to these alpha and beta fields, but nonetheless a U1 gauge theory in disguise. That if you focus just on the Poincaré waves, it is Maxwell-Chern-Simons theory, and they're responsible for the edge modes that are seen on the coast. It's also true to say that if you're interested in the way topology appears in physics, gauge theory is the right framework to work in. It's gauge theory where we found all sorts of wonderful, surprising, hidden structures to do with topology. I think it's fair to say that none of those more subtle aspects of gauge theory have played a role in this story so far. And so there's many open questions that I have. I have a few here. One thing I've utterly failed to do, despite quite a lot of attempts, is to understand how those equatorial chiral waves appear. And what's needed to do that is to take the Coriolis force and make it a function of space. Because as I pointed out, the Coriolis force to get the chiral waves has to vary over the equator. And so what I would love to do is get an effective action in terms of a gauge theory when F is a function of space. to try and understand that, what I called the Yanai wave in particular before. I've completely failed to do that. Other important points. There's some very basic topology in geophysics that all geophysicists completely neglect, which is the fact the Earth is round. Is that important? I don't know. Geophysicists think it's not, but is it? I'm not sure. The big open question, which I think geophysicists also agree is interesting, is does the topology survive in the nonlinear theory? So those coastal Kelvin waves have to be there for topological reasons. They're the edge modes of Chern-Simons theory. But if I do the full nonlinear theory, do they still exist, or do they somehow get washed away? I don't know the answer to that. And finally, just a general question: are there any other uses for gauge theory in fluids? There was a lovely paper by Shaheen, who's in the audience, a couple of weeks ago, who points out that something called Stokes drift in the shallow water equations can be associated with holonomy of gauge fields. It just sort of feels like maybe there's a lot more that we can say here. All right, I'll leave it there, but I'm happy to take any more questions. Thank you for your attention.
Thanks, David, for the nice talk. Are there any questions?
Yeah, so I just want to ask whether you get from the Chern-Simons term to the action that you had previously by integrating out some fields or integrating out some. Hello? That's
right. So I've got this action here. This is the linearized action.
Yeah.
That it is valid. Actually, this action is valid for any f of x. I said before that I would like to know what happens when the strength of the Coriolis force varies. This is the right linear action. The novelty is, though, it's got the E and the B, and also the P and the Q. Okay. And by solving it, has different branches of solutions, and as you can see here. And what I would like to do is, in a fixed branch of solutions, integrate out the P and Q and to get an action just for E and B. And I can do that just for the Poincare waves when I get Maxwell-Chern-Simons. The other branch of solutions has a different P and Q, and somehow I wasn't quite able to get an effective action for this flat band, even though it's the simplest thing. It's just a flat band. Did that answer the question?
Yeah, and also you have to get the A0 term. So that's another, I think, difficult thing to demonstrate in this language, right?
Where did I'm struggling to remember where the A0 term comes from. It's a step-by-step calculation of figure out what P and Q are on this band here, and just plug it back into the action. You see, it's quadratic in P and Q. So for once, I'm allowed to plug solutions back into the action, and you get the Chern-Simons term. You're right that it's a little bit odd about. There was some subtlety in the calculation, but it is a step-by-step calculation, and everything drops out nicely. Yeah, it's in the paper. Sorry that I can't give you a better answer, but it's in the paper.
David, there is a question in the chat. I can just read it out. Since the U1 gauge theory you wrote is nonlinear, can there be any solitonic solutions? If yes, what can be the physical interpretations of linearizations around these solutions?
It's a fantastic question. I've not looked at any solitonic solutions. Yeah, I don't know. I don't know.
Aren't the vortices related to the solitons in some way?
Sorry, say again?
Vortices. You had some vortices. You had vortices, right?
No, I had vorticity. Oh. Somewhat different. And you know, fluid dynamicists have vortices all over the place, but they're not topological solitons. Okay. So in the sense that we think of with some, pi 1 of U1 being non-zero. It's a great question. I don't know. Yeah, and if the question is, can we, my broader question was, can we find uses for gauge theory and the topology that we know of gauge theory? That would be a perfect place to explore that. Yes, it's a very interesting question. It's definitely one of the...
Just to understand the question, is the flat band just a soliton solution? Because it's time independent.
Yeah, in some sense, it's a weird soliton solution. It's certainly not a topological soliton, but it's yeah, in some sense, it's a soliton. But I think here the question was, could you use topology of the U1 gauge field to find a topological soliton? Yeah, it's a great question, well worth thinking about.
I think there are a couple of raised hands actually. Deepak, you want to go first?
Sure. I mean, I already asked a bunch of questions, so if somebody else wants to go first, I can wait.
I can answer all questions. It's okay.
The first question was that you're saying that you don't get these equatorial waves when you linearize the shallow water equations, right? So, I mean, people must have numerically integrated the shallow water equations without linearizing. Do we see equatorial waves in such simulations? Do you know?
I don't know. No.
Okay.
And the question is more, does the topology that protects these waves survive in the nonlinear limit? That's really the question. You see, you can always just solve the equations, and people did this in the 1950s and see that these things are there. The real question is there some deeper reason why they're there?
And the second question I wanted to ask is, I mean, like one of the major issues that concerns everybody pretty much is climate change, right? And one of the direct consequences of climate change is sea level rise. So is there any possible, you know, way in which this work or work of this type can help us understand the effects of sea level rise on coastlines and such?
You know, I would love the answer to be yes. The answer is yes. More than string theory is going to help us. I could say that. I don't. I suspect not. I've started talking a lot with fluid dynamicists because we have a bunch in Cambridge working on exactly these shallow water equations and applying them to climate change. And as far as I can tell, they couldn't care less about any of this. And they couldn't care less for very good reasons, because, you know, it's fancy maths and we're just having the luxury of thinking about these things, whereas they've got these enormous computer simulations that they've been coding for 20 years, and they care about the salinity of the ocean and, you know, just all sorts of horrible details that matter. So I strongly suspect the answer is, maybe I take back my previous answer. As much as string theory would help us is. Yeah.
Okay,
Rama.
a comment.
Yes, please.
Yeah, so I do fluid mech, and I thought I should put in a word on behalf of the oceanographers.
Good, please.
I think those guys know the Earth is round, but they have like bigger problems to deal with. For example, all the shallow water equations, the minute you add a bit of mean shear, or you remember that the ocean and the atmosphere are coupled, you get into very big deviations from these equations, which change the fundamental nature. Like, for example, shear will make the whole system non-self-adjoint. So I think they're grappling with those things. And the fact that the Earth is round is kind of minimal in comparison to those.
I was being flippant, of course, with
I know, I'm just joking.
the Earth is round comment. I'd like your opinion, Rama, that, you know, there are fluid dynamicists who are talking about topology in fluid mechanics, and as I said, my colleagues probably couldn't care less. Is that a general opinion?
Fluid mechanics, so people are very, very interested in topology in the game that I play with, which is small scale turbulence in terms of helicity. So how knots in vortices unknot and things like that. So topological things are extremely important there.
I see.
And yeah, I think it looks very interesting in this context as well.
Thank you. Thanks for your comments.
Sure.
Hi, David. Thanks for the nice talk. So I have a question. Can we think of the boundary theory at the interface of the landmass and the ocean as some sort of a 2D topological theory like Yang-Mills or something?
No, boundary theory is a chiral boson.
Okay, I see.
The
All right.
edge of a topological theory. So yeah, it's a rather trivial conformal field theory. yeah, is there any reason to think of it that way? I don't know. I don't know if that's useful. Part of what sort of confused me here was disentangling effects due to H-bar and effects due to topology. Because when we think about Chern-Simons theory and fractional quantum Hall physics, you know, H-bar is equal to 1, and it's sort of not obvious what you're thinking of as classical and what you're thinking of as quantum. So it turns out the story of edge modes in Chern-Simons theory is very much a story about the classical theory. You do not need quantum physics, even though the way we usually talk about it is anomaly inflow and things like that, which is quantum, but there's a classical version of that story. So yeah, you could well ask, what are the interesting classical things about, say, chiral bosons? I don't know. For example, in the quantum theory, the chiral boson has a radius that has all sorts of interesting things associated to it.
All right, okay.
Okay.
Thank you for that.
Are there any more questions?
I have a question, actually, David.
Please.
Yeah. You know, it's something, my fluid dynamics is quite rusty, but a long time ago, many years ago, people were interested in integral systems. So there's this Korteweg-de Vries equation, right, for shallow water waves, right?
The KdV, yes.
Yes. So what is the connection? I mean, is it that the Earth's gravitational field is neglected there, or that's a very nonlinear equation which is integrable?
That's right. Rotation. It doesn't have the Coriolis force, and it's a one-dimensional.
That's true. It's a 1 + 1. That is true. That is true. Yes, that is true.
So
Yeah.
possibly it's. I'm embarrassed to say I don't know. Maybe it's just a one-dimensional version of this where you throw away the Coriolis force and.
That
Rama, can you help me again?
To tidal bores and things like that. They are much smaller scale where Coriolis is unimportant.
Yeah, but the KdV equation is the 1D version of this shallow water without rotation.
Yeah.
Yeah. Okay. Thank you.
Okay.
Shaheen.
So do you have any comments on the Lagrange description? So this is the Euler description of the fluid, and where the question is what replaces the gauge symmetry there, and maybe something which is topological in this description becomes just a normal gauge conservation, or vice versa in the other one. Do you have any comments on this?
I don't think I have anything interesting to say. And as field theorists, we always are working in the Eulerian description, even though we don't know it. But in the fluids language, everything we do in field theory is the Eulerian description. So I guess your question could be asked more generally: is there an advantage to working in something closer to a Lagrangian fluid description for any field theory? Yeah, I don't know. I sort of, as you can tell in the whole talk, I learned something vaguely new and then tried to relate it to things that I already knew. But what I already knew was the Eulerian.
All right. And actually, as you may know, Lenny Susskind had a paper in early 2000s on quantum Hall effect and non-commutative Chern-Simons.
Yeah.
So I was wondering whether this non-commutative version would also appear here somehow. In Suskind's description, basically that the non-commutativity comes up because of the incompressibility of the quantum Hall fluid in 2 dimensions, whereas what we have here is 3-dimensional incompressibility.
That's right. I don't know. Yeah, I don't know. These are great questions. I have to say I don't know to nearly every one of them.
Okay, I have one question. I mean, as was being pointed out, the coupling with the atmosphere is paramount in such examples, right? Because the waves are created by the atmosphere. I mean, the dynamics with the atmosphere and the sea, the ocean, right? So is there any way you can incorporate that here or make any changes that kind of incorporate that sort of setup?
I did this calculation before Christmas. I went to a fluids course before Christmas and repeated everything in my language when it was possible. And so I'm struggling to remember what the story is. I think roughly speaking, any driving force which is Hamiltonian, non-dissipative, you can add to this description. And any driving force that's dissipative has some friction-like quality to it, you cannot. Because it's a Hamiltonian, because it's a Lagrangian, it's a Hamiltonian formalism. And I might be misremembering, it was some months ago. I think the most interesting driving forces on the ocean are not the one, cannot be incorporated in this framework because they're dissipative. Yeah, so sorry, I did do this calculation and I can't recall, but I think the answer is no, that the more interesting things have physics that goes beyond action principles. Loga, hey.
Yeah, so this is more this thing about this Lagrangian versus Eulerian. Isn't it just the difference between thinking about it from a world-line point of view as opposed to like looking at it from a field theory? So the corresponding question would be that does this Chern-Simons theory have some kind of a word-line description? Right? Is that a correct way to phrase that? Or
Possibly. So the velocity is roughly speaking the electric field, and somehow in the Lagrangian perspective, you want to follow, elements of the fluid along. But now along with the electric field. So I don't know. You've thought more about these kind of things than I have, Loga. But it's not obvious to me that it's just a question of you want to. Yeah, I don't know what the elements of the fluid are for the electric field. It's world lines of test particles, maybe. I'm not sure.
Okay. Thanks.
Hi.
So-
now that you have an action formulation, can't you put this at finite temperature and do a path integral? And does that tell us anything interesting about the ocean?
I can absolutely do that. I've no idea if it will tell us anything interesting about the ocean. Yeah, I did think about, can you do stat mech on this? And is it, if the ocean boils, maybe it's interesting. I don't know. It's certainly something you can play with. There's a lot to play with here. And as we've heard, probably most of it is not interesting for fluid dynamicists, but actual geophysicists, but it may well be interesting for more conceptual reasons.
Thank you.
And is there any way you can incorporate turbulence? Can you see turbulence coming out of all this?
No, it's in there, but I know it's in there only because my fluids friends have done simulations on shallow water equations and sea shock waves and sea turbulence, but it's not like the action helps you with that.
Okay.
There are no more questions. No. Thanks, David, for the very nice and interesting talk.
Thank you very much.
Thank you, everyone. Nice to see you all.
Yeah, thank you very much.
Bye.
Hope to see you in person sometime soon.
Yes.
Can I quote you on that? What you said about string theory and climate change?
What you can quote me on anything you like, but yeah, what did I say? That it won't be useful? I don't think that's controversial.
True.
Okay, bye all.
Bye, Aaron.